What we're going to do today is we are going to examine the idea of hydrates. So I've got myself a scale here, and I have got myself a crucible that is empty, and I've got myself a bunch of alum crystals that are there. So what I want to do is I want to figure out what the formula for those are. So I'm going to need to take some data. The first thing I'm going to need to know is I'm going to need to know what the mass of this crucible is when it's empty, because I'm going to have to subtract it out later. So I'm going to go ahead and hit tare just to be sure. And then I'm going to go ahead and put that crucible on there. And that crucible is telling me it's about 12.6 grams. Okay, good. That's good to know. And now what I'm going to do is I am going to once again tare it, but I'm going to make sure that I write that number down, that 12.6 grams. That's an important one. But I'm going to tear it out so that I don't have it anymore. And now what I'm going to do is I'm going to put in some alum crystals here. And I'm going to put in some alum crystals and see what those are as far as their mass is concerned. So apparently it's about 6.6 grams of my alum crystals. Once again, I am going to write this guy down. Now these alum crystals have the water in it. What I am going to do is I am going to take these and I am going to heat them here in my flame. And in doing so, I will drive off the water and the mass will go down, and I'll be able to then figure out what the mass percentage and the hydrate is for that. But we can't hold this in our fingers and do this. That doesn't make any sense. We need to set up a safe device and a safe way to do this guy. All right, this is our setup for our triangle in order to heat a crucible. I've got a ring stand here, and that ring stand is connected to an actual ring. And on top of that ring, I have what's called a triangle. And this guy here, you can unscrew this and move this guy up or down as the case may be. But when you do this, this guy here is designed to hold your crucible that has whatever it is in it that you want to heat. So this guy here is going to be a perfect setup for us to check out with our Bunsen burner flame. So now I've got my Bunsen burner flame, and it is set up underneath my alum crystals that are there. Now if you take a look at it, the flame is actually pretty far away from the bottom of that crucible, and that's no good. So what you want is you want to make sure that the bottom of the crucible here, this guy here, is just above the hottest part of that flame, which is the tip of that cone. So I am going to set this down here and see if I can't drop this level. And in dropping that level, I now have the tip of the Bunsen burner just below the bottom of that I have the tip of the Bunsen burner just below the bottom of that crucible. And if you check it out, there is some serious bubbling and churning action going on there. So can you see that? I am definitely heating the heck out of those alum crystals. And you can tell that the water is being forced out of the compound. So we're going to let that heat until it is good and done. And then we will let it cool and we'll check its mass again. Next, what we want to look at is how we are going to manipulate this. The right tool for the right job. You will probably find all of these devices in your lab drawers, and you may be tempted to use one or more of them at various points. But let's make sure that we use the right tool for the right job. First of all, this guy here has rubberized ends, plasticized ends over there, and if I were to use them over here on something really, really hot like a flame, those are going to burn. So that's no good for this. These are beaker tongs. These are designed to get something big like a beaker here and hold them steady. So that's not what we want. Next, you might be tempted to use these guys. They look kind of squeezy. I could grab those. There's no plastic on them, except these. The only point of these guys is to do a test tube. So these guys go and they grab a test tube and they use them, to move a test tube around. That is no good. So our third choice is going to be these guys. No plastic end. It's got nice grippy ends there, and so if you need to use this guy, all you do is you come over here and you grab this guy by the edge like so, and you can move him around all you want. All right, so these guys here are your best tongs to use for this application. All right, our alum is just about dehydrated here. You can see it's gone from looking like these crystal thingies here, right? They kind of look like salt crystals, to more of a globular, molten paste more than anything. The bubbling has certainly stopped almost completely, not maybe entirely, but we'll give it a couple more minutes. And then, of course, we got to let it cool down. So even if at this point we come over here and we turn off the gas, it'll continue to cook for another couple minutes. Like I said, you do not want to touch this yet. This has been in hundreds, if not 1,000°C heat. It is going to be hot. In fact, the number one cause of injuries is students grabbing things after they have been in the Bunsen burner and burning themselves. Now you think to yourself, well, no problem. I will just use the tongs that you told me to use, and I will pull this out, and I will, well, that's all fine and good and so forth. You can do that, but what you can't do yet is you can't weigh that thing yet. Why? Well, let's look at the scale. What is this scale made of? This scale is made of plastic, and this scale is made of thin metal parts. What's going to happen if you put something that is 1,000 degrees on a scale like this that is made of plastic and of thin metal parts? Well, it's going to melt. So you can't do that. You have to give this 5 minutes or so to cool down. And you know that it's safe to actually come over here and weigh this guy, use the scale. You know it's safe to put this guy onto this guy once you can touch this guy with your bare fingers and not get hurt. A little warm is okay, that's fine. But if this guy is so hot you can't even touch him, then he is not yet ready for the scale. All right, this is now cool enough for me to touch with my hands without being burnt. I mean, it's still a little warm, but that is okay. So now what we're going to have to do is remask this guy. So I'm going to come over here and turn this on. And then I'm going to make sure I hit the tare button just to be sure. You always make sure that you're in grams, right? The little G down there. And now all we have to do is put this guy on here like so. And this is telling me that it is 16.1 grams. Now what we need to do is figure out how much water we lost, and therefore we can figure out what the formula of this is. So that is your third data point that you need to write down. 16.1 or 16.2 is the number of grams of the anhydrous material with the crucible, the two of them together. Because remember, we're going to have to subtract out the mass of the crucible to figure out how much of the anhydrous material is left, because we don't want the crucible. Let's dig into the math of this and see how we did. So our job is to try to figure out what the formula for alum is. Alum has the formula that is listed here. It is potassium, aluminum sulfate, like so, with a certain amount of waters attached to it. And our job is to figure out what this guy here is. How many waters are involved in this crystal? Is it 1 water for every potassium aluminum sulfate? Is it 27 waters for every potassium aluminum sulfate? How are we going to do that? Well, remember, in our discussion of empirical formulas, what we are really interested in is we are trying to figure out the moles of the potassium aluminum sulfate and the moles of the water. And as soon as we figure out the moles of those guys, we can figure out what their molar ratio is, and therefore we will then know what the formula is. Now to do this, we needed our 3 data points. And our 3 data points are, first of all, the mass of the crucible with nothing in it, the mass of the hydrate, which is everything included. So all of this is the hydrate. The potassium, the aluminum, the sulfate, and the water, that is basically the before. So the mass of the hydrate is your before heating. And then, when we were all said and done, we have the mass in the crucible and the anhydrous material. And the anhydrous material is just this, because the water has been driven off. Because remember, by heating it, we are taking the water and we are driving it off. So the anhydrous material is just the potassium aluminum sulfate. that's there. So basically what it comes down to is this is kind of the mass after. This is after heating. So what we need to do is figure out what the moles of this guy are and the moles of this guy are. And these are our three data points, 12.6, 6.6, and 16.1. Now, let's do some calculations and figure out what's what. So we come down here. What was the mass of the hydrate before? Well, before we did anything, it was the 6.6 grams. And that is the salt and the water. Now, what is the mass of the anhydrous material afterwards? Well, if you put 16.1, that doesn't make any sense because that would mean that it went up in mass. But remember, this 16.1 is the crucible and the anhydrous stuff. I just want the anhydrous stuff. So I'm going to have to make sure that I subtract out the mass of the crucible, which is why that was the first thing that I did. So if I subtract out 12.6 grams from this, what I really end up with then is 3.5 grams afterwards. So the mass of the anhydrous after is 3.5 grams. So the salt I started with was 6.6 grams. After driving off the water, I'm down to 3.5 grams. So how much water did I lose? Well, if I simply subtract those two numbers, I get 3.1 grams of water of the H2O that I lost. So I now have the two numbers that I need. I have the 3.5 and the 3.1. Now, if you went and tried to put those numbers into here for X and Y, you'd be wrong because the 3.5 and the 3.1 are the grams, and we need them into moles that are there. So I need to take each of these substances and divide them by their molar masses to figure out what their moles are. So what are the moles of the potassium aluminum sulfate going to be? Well, the first thing I need to do is get out a periodic table and add up a potassium, an aluminum, 2 sulfurs, and 8 oxygens that's there. And if I add all of that up, and again, I have 1 potassium, 1 aluminum, but because this is in parentheses, I have 1 times 2 is 2 sulfurs, and 4 times 2 is 8 oxygens. And if I add all of those guys up, this guy here has a mass of approximately 258.3 grams per mole. So, how am I going to get the moles of just the anhydrous salt with no water in it? Well, which of these numbers, here or here, which of those numbers is the one I'm going to use? Which one represents the anhydrous salt? Well, that's this guy, the 3.5. So if I have 3.5 grams of the potassium aluminum sulfate, and I divide it by its molar mass, 1 mole per 258.3 grams, I end up with, roughly speaking, 0.0135 moles of this guy. So that 0.0135 is the number that is going to go here. 0.0135 that's there. That's how many moles of just the salt that I had. Well, what about the water? Well, remember, I lost 3.1 grams of water. So I need to know the molar mass of water. Well, water is an easy one. That's 18 grams per mole. So if I have 3.1 grams of water and divide it by its molar mass, 1 mole per 18 grams, I end up with 0.172 moles of water. And so that number there is going to be my number of moles of water that I have here, and that is 0.172. So now what do I do? Well, if I check out the two numbers that I have here, I want them to be as close to a whole number ratio as I can. So remember, what you do at this point is you pick whichever of the numbers is the smallest and you divide by that number. So it looks like the 0.0135 is the smallest. I will divide by 0.0135. And when I do that, 0.0135 divided by itself obviously gives me 1. So that number there is 1. And for the water, if I divide those guys out, I end up with an answer of 12.7. Now, this is supposed to be a whole number, so it's probably between 12 and 13, depending on experimental error. So using our data, we got 12.7. Now, what is the correct answer for this? Well, it turns out that alum has a formula of potassium aluminum sulfate with 12 waters. So that is the answer that you were supposed to have gotten. 12 waters. We got 12.7, which is pretty darn close.